Let's go ahead and move into the last talk for this session. Let it quiet down a little. Awesome, cool. So I did ask Erick, if he could tell me some interesting things about himself. And we struggled actually a little bit, but he is someone I empathize with very much. We thought about training a Markov model on his activities and found the surprising fact that he exists in exactly 2 states between his day job and his PhD. So with that, I'd like to introduce Erick.
Okay, cool. Yeah, I like talking into things, so I'll just do that.
Okay.
Here, I'll pass it off to you. Awesome. And actually, we did miss 1 state. I also have 3 children, which is roughly 1 million once you extrapolate for activity level. So it turns out to be 3. Cool. So hi, everybody. I'm Erick. That was a great introduction. It's the best one I've gotten at this conference so far. And I'm going to talk about what is the shape of an executable, which is a bit of a misnomer. I'm going to talk a little bit more about how transfer learning is real, but we'll get into it. So I can mostly skip this slide because I've already been introduced, but let's kind of get into the motivation, right? Like, why did I even start looking at this? And there's a lot of good labeled PE samples out there. A lot of good ones for Windows. There's this data set called Ember. Some of you might have heard of it. It's pretty good. But there's no such thing for Mac or for Linux, right? You can pull samples if you want. You can, put up a live hunt rule on VirusTotal or whatever, but there's no good labeled data set for Mac and Linux malware. And so it makes it tough to train machine learning models because, as we all know, labeled data is pretty crucial, right? So one of the things I asked myself is there a way we can use all of the stuff that we know about malware analysis, which is maybe a little bit more specific to Windows, and extrapolate that data to Mac and Linux? And I was really inspired by a paper by Ed Raff, who is on the program committee. I don't think he's here today, where he used a convolutional neural net to write a malware detector. And so I was thinking, that seems fruitful, right? I don't have to do feature extraction. Transfer learning exists. And I wonder if there's something around the filter shape that we could use. And so I looked at a paper by Lee and found that there actually is a way to compute in an optimal shape for a filter, or we would, support of the kernel, right? So a brief aside on Windows PE files, they're based on the common object file format. Incidentally, so are ELF binaries, and so are Mach-Os, which means that structurally, in a very abstract sense, they're all cousins, right? One of the other commonalities that they all have is that courtesy of Apple switching from PowerPC to Intel, they're all compiled for the same architecture, which means that the actual bytes that get passed to the processor and the ones and zeros are not the same, but they're similar, right? Movie AX looks the same. I guess you wouldn't, whatever. So, right? So then we look at control flow graphs, right? And that's kind of how we get to shape. Is we know that you can represent an executable as its control flow graph, right? I think we just all listened to a really great presentation on graphs, and I don't need to belabor the point. I think you all believe that graphs exist. Right? And so going back, why use a neural network? And it all comes back to that transfer learning. We don't have a lot of labeled data, and it takes a lot of time to build a labeled data set, we all have jobs. I mean, maybe some of us don't, but we probably do. And like, I don't have a couple of weeks to collect a good data set on top of all of my other responsibilities, unless I make that one of my responsibilities, right? So if we can inherently learn what the features of malware versus benignware are, then we don't need to hand engineer features, right? This is aspirational. I would love to live in a world where you could just take a PE file or a Mako or an ELF and just throw some linear algebra at it, and out pops a 1 or a 0, and it's right all the time. I think that would be great. This is my training environment. It's boring. We don't care about this. Yeah, this whole thing is boring. Right? So this is my architecture. And actually, this slide, I really do want to drive home how interesting it is that a boring architecture can yield good results. Because one of the things that we look at a lot is we look at the BERTs and we look at the XL nets and we look at the GPT-2s and we look at, the image, not ImageNet, right? The ResNets and whatnot. And they're huge. They're mammoth. And so starting from a very simple sequential architecture, it's more how does this methodology operate rather than if I add a few million more trainable parameters, can I overfit a data set well enough to get accuracy results that people want to read? But it works for our purposes, right? Because I'm not interested in, I wasn't trying to get a 99% accuracy rate. I'm really trying to see, does it transfer, right? So to kind of jump back into that transfer, we wanted to generate this filter shape because, right, in a standard convnet, you have these rectangular filters. If you write your keres.conv1d, you get a rectangular filter of whatever size you specify, a 3x3 or a 5x5 or what have you. But in this Leodow paper, what they do is they find that repeated applications of a lasso regression can show you what the support of the kernel is and what the shape of your filter ought to be, what the optimal filter to learn on is. So you start with a set of filters, and these are filters that have been trained on your data. And at the end of each epoch, what I did was use a covariance matrix that was the same size as my filter based on random samplings of the data set to get this filter shape. And it was extremely time intensive. It took about 4 hours at the end of each epoch because we did it for every single filter in both convolutional layers at the end of each epoch. And after about 60 hours of training, it turned out we didn't really need to do that much. So the filter on the far right is the filter mask that we ultimately ended up using and was the last training mask generated at the last epoch. And we found that when we generated them for Linux and Mac, they were very similar, right? Not perfectly similar, but close, suspiciously close. Especially between Mac and Windows, right? Our Linux data set was maybe a little too heterogeneous, and I'll talk a little bit about that later. But the similarity between Mac and Windows was really striking. The other thing that was really striking to me was that when we were training and saving these masks off at the end of every epoch, they looked really, really, really similar every single epoch. And so we have a filter that was generated by the first convolutional layer at the end of the first epoch, a filter that was generated by the first convolutional layer at the last epoch. And they had a cosine similarity of 0.9484, which is pretty close. and suggests that we wasted probably like 54 hours of training, which is great. That's great. It's great to know now that we don't have to do it again. Everybody can just use this mask. You don't have to worry about it. And so the testing results are not great, right? I think that's fair to say. So we tested against the Ember benchmark and we tested against Malconv. Both models were graciously provided by Endgame, so thank you to Phil and Hiram and everybody else who worked on that and made those publicly available. So we found that vanilla Malconv did not perform very well on the Ember 2018 test set. And we performed a little bit better, right? But what I really want to draw attention to, and what was interesting, was that we ended up with a not at all production grade, roughly 72% accuracy. Again, not good. But without any additional training, we passed the MAC samples that we collected to the exact same model. No additional training, just said, hey, predict these. And we got pretty close accuracy, really close. A little bit worse on Linux, just pretty terrible. And then training just the output layer on the Mac and then the Linux, we improved our accuracy a little bit, which makes sense. That's a 0.774. So it's actually better than our accuracy on Windows files, which happens. Small sample size. Boy, that was quick. So, right. So the training overhead was extremely cumbersome, right? The training time in general was extremely long. It was about 25 hours per epoch, plus the 4 hours to generate the filter shapes. So it came out around 30 hours per epoch, which is a lot. But what I really want to drive home, right, and slides can only say so much, is that I think that what we find here that's really interesting is that without any additional training, it got that similar accuracy. And I wonder if that is due to, right, the instruction set, the similarity in the COFF-based architecture. It suggests that there is an underlying structure to all of these x86 compiled binaries that would allow us, if we can figure it out, to exploit it and make it so that we don't need to generate these gigantic corpuses of corpora of Mac and Linux executables. We don't need an Ember for Mac, even if we want one. But maybe we can write a classifier that's a bit more general. And if we could write a neural network-based classifier that actually managed to outperform the Ember benchmark for once, it would be a tremendous step forward. So I would really like to gather more samples, and I'm working on that. I'm also testing an alternative architecture right now, because while a very, very simple model is great for demonstrating that something works conceptually, having a model that's a bit more complicated is the wrong word. Having a model that's a bit more robust, a bit more clever, might yield acceptable results rather than passable results. So yeah, I think that's really it for me. Kept it short and sweet for you.
All right. Once again, we have the microphone for questions, so if people could raise their hands.
Hey, that's fun and really surprising, shocking. I'm wondering if what you would suggest doing to try to tickle out why this commonality might be the case. Like,
yeah.
what kind of analysis that you could do?
So, right, my inclination, coming from a background as a research engineer and a malware analyst, is that I want to analyze by hand some sample of the misses and the correct classifications and see kind of where those similarities are. That's not a scalable solution. I think that testing on a larger set of Mac and Linux executables would help tease that out a little bit. I also think there's probably a bit that I could do in comparing against other test sets on the Windows side, right? I think those are sort of the big things that I would want to try. But yeah, I found the results really curious as well. I wish I had a better explanation for you, right? My working hypothesis is that they're compiled for the same instruction set. And so there's just something about that instruction set and underlying structure that makes them sufficiently similar. But that's my working hypothesis. Maybe
Great.
next year.
Very interesting talk. Thank you very much. I just wonder, have you considered taking a look at binaries that are cross-compiled, probably from the same code base across the different architectures? So taking a look at like commonly available things like that are available for all platforms are probably compiled from the same code base and would have similar call trees apart from maybe the library calls that they're making for the different architectures.
Yeah, so I think that's actually a really good suggestion. One thing that we did do was try and make sure that we had as much heterogeneity in the data set as possible. So we looked for things that likely weren't cross-compiled. But if we had a sufficiently large number of samples that were cross-compiled, that may actually answer Hiram's question.
Once you transferred the training to the Mac and Linux binaries, did you then evaluate the performance for the Windows PEs again? So did it forget that original task, or did it remember some level of performance?
So when we did the initial testing, there was no additional training at all, and so I didn't test the same model against it, but it was the exact same model with the exact same weights, so presumably it wouldn't change, it better not change the outcome. I did not test it again after training on Mac and Linux, but that's a good idea. I'll do that this afternoon. I'll let you know how it goes. Put it in the pipeline.
Did you look at any correlation between the tool chain and the sample shape? So for example, if it was like a Delphi compiler versus Visual C?
Well, as we all know, Delphi is an indicator of maliciousness. So I tried. I'm glad that, that didn't go over anybody's head. No, I didn't look at that at all. Really, my goal here was to be as naive as possible, which is like, what is the dumbest, most boring model that can learn something interesting? Was really the goal here, right? Essentially, it's really, really easy to get good results if you have like smart malware analysts who tell you what features to use, and you get a nice data set and you put those features in. The goal here was to say, like, what can a neural net learn with no additional information? I think that adding that information would probably get me to the sorts of accuracy results that people would be like, oh, wow, that's not a garbage network, right? Instead of where we are now at 72%. But the goal here was really to be as naive as possible and just let a model that knew nothing, had no information, and no metadata learn something.
Cool. Do we have any further questions?
Just to follow up on the previous question, my understanding what you just said and what he was saying was that depending on like what you're actually really learning, what I think is actually learning where you got the errors, because it could be possibly that the compiler is what you're training on, right? So if I compile and for Windows stuff, it's more like a Visual C compiler versus like Linux where it's GCC or Clang, and so I think that's what he's getting at. and that was the point. So I just wanted to make that
Yeah,
comment.
I'm sorry, I must have misunderstood the question.
All right, last question, and then I'll hand it back to Hiram.
Thanks. What kind of hardware did you do the training on?
So I wrote this slide.
Oh, gotcha.
Tried not to talk a ton about hardware and software. I spent way too much time on it when I was practicing. Maybe there was a little griping in there. I don't know. But so, yeah, the hardware that I trained on was actually pretty decent. I only used one GPU because it's a shared rig. But really the bottleneck here was this awesome USB external hard drive, which, you know, the throughput on that was less than optimal. So that was pretty good. I wrote the whole thing in TensorFlow too, so, you know, pretty proud of myself for that one. Because that didn't go live until like a month ago. It was, yeah, we did beta, so that was fun.
Cool. Let's give Eric one more round of applause.